Panda's plotting interface simplifies producing a wide range of data visualizations. Here, we focus on two common methods used to understand data and their relationships: histograms, which visualize the distribution of a variable, and scatter plots, which show the relationship between a pair. We conclude this lesson by examining the options available to export figures. Start by opening the Lesson 22 notebook. I am using PyCharm in this demonstration to highlight some of its features. Let us start by running the setup cell. We need to call this IPython magic whenever we plot in a Jupyter notebook. This command ensures that plots appear inline in a cell's output. We need to load the high-frequency data that is stored in an HDF file. We need to import pandas and use read HDF. Read HDF takes two inputs, the file name and the variable's key. These values are hf.h5 and IBM. We can assign the output of the read HDF function to a variable, which I call IBM. The command to load Microsoft's price data is virtually identical, only using a different key. We can see that these two series have been loaded in the Variable Explorer. Clicking on View as Series displays the data in the SciView window. We can see that the data are all prices from a single day. We can close this view and move on to the first problem, where we are asked to produce a histogram. Plot.hist visualizes the distribution of the values of a variable. While there are no required inputs, two keyword arguments are common. Bins sets the number of bins used, and density ensures that the bin heights are normalized to sum to 1. Plot.hist is a wrapper around matplotlib's hist, which documents the full set of options. We need to compute 1-minute returns. Pandas contains a sophisticated method to resample a time series. The resample method requires one argument, the new sampling frequency. We want 1-minute returns, and so we use the string 60s for 60 seconds. This creates a resampler, which then needs to be told how to transform the prices in the window. When computing returns, we want the final price in the window, which is accessed using the last method. Running the cell shows the output of the resampler using the last aggregator. These are 1-minute prices. We can call %change on the last prices, and then drop NA to remove any missing returns. We can create a basic histogram using rets.plot.hist. Running this cell produces a histogram with 11 bins. We can use setTitle on the axes to set a title for the histogram. I prefer to scale by 100 to get percentage returns, but this is a personal preference. Customizing the number of bins is the most common tweak to a histogram. We can change the number using the keyword bins. First, let's set it to 51 and rerun the cell to see the new histogram. This produces a very jagged image, which suggests that we have too many bins. We can try a smaller number, 21. Running this configuration produces a more balanced histogram that shows the details of the distribution without being excessively jagged. Pandas plotting supports plotting kernel densities using the method KDE, which is a smoothed version of a histogram. The next problem asks us to produce a scatter plot of the returns of IBM against the returns on Microsoft. Plot.scatter produces a scatter plot of two variables. Two inputs are required, x and y, which contain the column names of the data to plot along the x and y axes. Other common keyword variables include marker, which sets the marker used, S, which sets the size of the marker shown, and C, which contains a color. This function wraps matplotlib.scatter, which contains a complete description of the available options. First, we need to construct 5-minute returns. Here we use resample again, this time using 300-second samples, and use last to get the final price in the window. We can then call %change on the resampled prices to compute the 5-minute returns. After the two return series are created, we need to merge them into a single data frame. The dictionary syntax, where the column names are used as keys and the data series are used as values, is simple to use here. We can use head to look at a few rows from this combined data frame. There's a missing observation since the first price of Microsoft occurs after 9:30. We can use drop-NA to remove the missing observation. We then call combine.plot.scatter. There are two required arguments, the column names for the X and Y columns. Running the cell produces a basic scatter plot. I do not like the margins on this plot, and we can use setXlim and setYlim to change them. Figures expose many properties that can be used to customize their appearance. The most common are methods that are attached to an axis. Properties are changed by calling the method setProperty, where property is a descriptive name of the property being changed. Common properties include xlim and ylim, which change the range of the values shown, xlabel, ylabel, and title that label axes or set the title, xticks and yticks that set the location of the tick markers, and xtick labels and ytick labels that change the labels shown on the ticks. Each property is mirrored by a get property that returns the current value of the property. We can get the largest absolute return using combined.abs.max.max. setXlim is used to set the range of values shown on the x-axis. We set the limits to minus bound and bound. Running the cell shows that the x limits are now tight. We can also set the y limits to the same values. While the maximum absolute return is a safe bound, I like to use 110% of this bound so there's a small margin around the points shown. Running the cell shows that the points fill most but not all of the plot. We can use Seaborn to improve the default aesthetic of the plot. The dark grid set of defaults improves the appearance of the ticks. We can also change the figure size using plt.rc, figure, and fig size equals 12,8. Rerunning shows that the plot is now a reasonable size. We can change the marker using the keyword marker equals x. I also use s equals 64 to increase the size of the marker. Running the cell one final time produces the ultimate version of this plot. SaveFig export figures to one of many common formats, including PDF, PNG, JPEG, and SVG. Only the file name is required. The file type is automatically determined by the extension of the file name given to SaveFig. The set of optional inputs depends on the output format. PNG, for example, supports DPI, which improves the smoothness of an exported image, and transparent, which removes any default background color. SaveFig is most commonly used as a method attached to a figure. The figure object is accessed from an axis using getFigure. We can then call SaveFig on the figure to export to a PDF. We can also use SaveFig to export to a PNG. PNGs support additional keyword arguments, including DPI to set the DPI, which improves appearance, and transparent, which sets the background to be transparent. We can open the PNG in PyCharm, and we can see that it contains the scatter plot produced and has a transparent background, which is indicated by the checkerboard appearance. We can inspect the exported PDF using an external viewer. This lesson introduced histograms and scatter plots. Histograms visualize the distribution of a variable. Histograms require no additional inputs, although it is often useful to explore changing the default number of bins. Scatter plots show the relationship between two variables and require two inputs, x and y, which are the column names that contain the data to plot along the x and y axes. SaveFig is used to save figures in a variety of common formats, including PDF and PNG. SaveFig is called from a figure instance, which is simple to get from an axes object. Finally, we saw how setProperty is used to customize aspects of figures, including setting the range of values shown, adding labels, and setting a title.